Well, good afternoon, everyone. Super excited to see all of you. I'm Cody Coleman. I'm a co-founder of Coactive AI, and I serve as the CEO. And I'm super excited to be here today to tell you about how to grow and compress data sets as part of the introductory course to Data-Centric AI. So, in thinking about it, also I probably forgot to mention the most important point. You know, I'm a fellow MIT alum. I did my bachelor's and master's degrees here at MIT in 6.2, and then went on to do my PhD at Stanford in computer science. So it's really good to be back and to see like a lot of familiar places and things like that. So in today's lecture, we're going to kind of focus on or come back to labeling and pieces of labeling. So already in the first lecture on data-centric AI versus model-centric AI, we talked about why care about labels and care about how we create data sets. You know, the importance of and the shift kind of in the ML field to focusing on data in order to actually be able to have kind of practical advances and improvements. In the lecture on data set creation and curation, we actually talked about like who labels and how do we actually do that to be able to create high quality annotation and information for data sets, given like an example that we want to label. And today we're going to talk about what do we label, and specifically we're going to look at methods in active learning, which will kind of intelligently select which data points are the most valuable or informative for us to label. Given like a large amount of unlabeled data. And then on the flip side, if we're in the case where we have a lot of like labeled data or just a lot of data in general, how can we compress that down into a smaller, more representative set called a Corset selection? So in the first part of this talk and in this lecture, we're going to focus a lot on active learning. So why is selecting what to label important? So when we think about actually the labeling process, it can be really, really expensive depending on the task that you're doing. For example, in speech recognition, annotating at a word level can take up to 10 times longer than the actual audio recording. And if we want to do fine-grain annotations, it can take up to 400 times as long just for a single annotation on that audio clip. And we see similar things in relatively straightforward tasks like name entity recognition and information extraction. We're even locating kind of entities in simple newswire stories can take a half an hour or more, just in these like simple cases. So this adds out to be just a massive amount of time as well as also like cost when we think about the labeling process. And then if we think about kind of the data set creation and curation process where we might want to have multiple annotators label the same thing, the costs really grow from there. Now, if we're actually smart about what we're selecting, we actually don't need to label as many things. So this is a simple graph of doing binary classification for a few classes in ImageNet in a one versus all setting. What we can see is if we had all of the data, we get the dashed gray line up top in terms of mean average precision. If we did random sampling, so we just picked examples at random and we labeled those, we get the blue line, the solid blue line at the bottom. But if we actually do this process of active learning, where we're a little bit more intelligent and we adapt adapt based off of our model's uncertainty using a technique called maximum entropy, we can actually get massive improvements in the mean average precision that we want with the same amount of labeled data. So as you can see here, just like the gap between the blue line and the orange line, we can get massive improvements very, very quickly by doing active learning. So what is active learning? So the goal of active learning is to find the best examples to label in order to improve model performance. And this is done through an iterative process where we start off with a large amount of unlabeled data. So this can be provided to us like by any process in the world. And then we take some kind of small amount of that, some subset, maybe it's given to us, maybe we do a random sampling or some other thing. We take this kind of small initial subset and we label those examples from our unlabeled pool. And then with this initial labeled set, we actually train a model on this kind of small subset of labeled data. And this is where the adaptive part comes in. We actually take that model that we've just trained, and we apply that model with some selection criteria or selection strategy to all of the examples in the unlabeled data set to be able to actually quantify the informativeness or the value of those data points. And then once we have this kind of metric or value for each one of these individual unlabeled data points, we can actually select the most valuable ones for us to label. Then we actually label those examples. And then we repeat this process. So now we have a slightly bigger labeled subset that we train our model on. And we can keep repeating this process of iteratively applying our model to all of the unlabeled data to quantify the informativeness, selecting the most valuable things to label and training a model on it over and over and over again in this iterative kind of adaptive process until we reach some stopping criteria, like we've exhausted some labeling budget that we have. At which point, we have our fully labeled subset of the data, and we can train our model kind of one last time on that full subset of data to actually use it for the downstream prediction tasks that we care about. And of course, we can always kind of continually pick up this process and label more data as needed, or as we find kind of other things that are uncertain in the wild. So to actually just like write this out from like a pseudocode kind of example, if we think about it, we start off with some initial labeled set. So where's the, oh, perfect. Awesome. So we'll have some initial labeled set that will make our labeled data. So LR equals LR not. So that's that seed set that we just talked about. And then we'll have some pool of unlabeled examples for us to pick from for selecting. And this kind of initial pool is going to be all of the, is going to be the set of our examples from our unlabeled kind of master pool that exists in our unlabeled pool and are not in our initial labeled seed set. And then from there, the process is actually pretty straightforward with these two sets. What we do is like, while our labeled data set is less than, the size of our labeled data set is less than some kind of labeling budget that we have represented in T, what we do is we train a model. So we'll call our model A of R, or AR. And we train a model on this kind of currently labeled set. And then once we have this model, we can then find the maximum example of our kind of candidate pools to label from. So we want to find the argmax. The argmax X that exists in our candidate pool to label using some selection criteria phi that takes in each example X and our model. So we're applying our model and some selection criteria to all of this in order to get the argmax of it, which we call X star. And then with X star, we can actually just go and update our label pool by taking kind of our existing labeled examples, and we now union that with one additional example, which is X star, comma, the label of X star. And then what we want to do is to make sure that we don't end up selecting the same example over and over again, we also update our candidate pool. Where now we remove X star from that candidate pool. And this is kind of the baseline algorithm that we just described there, this iterative process where we're training a model, we're finding the maximum kind of most informative data point out of our entire unlabeled pool, we're labeling that, and then we're kind of removing it from our candidate pool, and we can repeat this process over and over. So a relatively straightforward algorithm, but it can actually lead to massive speed ups in practice. And to actually see this, we can do a simple 1D example. So let's say we're in the case of a one-dimensional line where we have two linearly separable classes. On the left, we'll see an active learning approach, and on the right, we'll see a passive learning, or where we're doing random sampling. In both cases, we start off with the same initial seed examples and the same pool of unlabeled data. So the unlabeled data is shown in gray, and then the two classes are red and blue. And then what we see is kind of right off of the bat with active learning, it basically figures out to bisect the space in between the two labeled examples that we have so far. So we see that it says that we should select the example that's right in the middle, this red dot. Whereas passive learning or random sampling, we have no control over that. So it's going to pick a data point for us to label at random. And then if we do another iteration with active learning, we see that it'll bisect it again in terms of the uncertainty. And then we end up with this kind of new blue point where, again, with random sampling, we were unlucky. We're not getting actually that much more of an informative point. And we can repeat this process kind of for a few more iterations. And we see that very quickly, the active learning procedure is effectively doing binary search to really hone in on what is the true decision boundary, which is represented by the dashed gray line here. Whereas with passive learning, it's still not really getting to it. We're unlucky in this kind of setup. And we find that in 6 iterations, this active learning strategy is already at the point that's kind of honed in on what the actual decision boundary is. You can see that by the blue and the red dots at the center actually overlapping and creating purple. Whereas the passive learning strategy with random sampling is nowhere near this decision boundary. And in fact, active learning can give exponential speedups. So this passive strategy will reduce the error proportional to 1 over n, whereas an active strategy can reduce the error proportional to 2 to the minus n, or so an exponential speed up in comparison to just the normal passive strategy. And we can actually run this example even further for more iterations. So if we ran to 25 examples compared to where we were with 6 examples from the active learning strategy, we see that still the passive strategy is nowhere near as far as close to honing in on the decision boundary. If we run that for another 25 iterations, we're still nowhere near the actual decision boundary. 75 iterations, we're still not as close as we got with active learning with 6 examples. And it's not really until we get to 100 examples of just randomly selecting that we even get close to this decision boundary. So you can just see the power of how active learning can provide exponential speedups, saving you from having to label all these extraneous data points. Question? Yeah.
Yeah, I have a question. So I'm looking at so passive learning requires more iterations, but in my understanding, each iteration is just kind of one computation, whereas an active learning for each iteration you compute the argmax, which isn't that technically O of the magnitude of your unlabeled space. So how would active learning overall result in less computations? That makes sense.
Oh, yeah, sorry. I might have misspoke there when I said that active learning would perform less computation. It will save you from labeling as much. So so this is a super great question. So it will save you in terms of labeling costs, not necessarily in terms of computation costs. And this is actually one of the problems that we have with active learning in practice, is because for very large data sets or models, it can actually be kind of intractable, which I'll talk about in actually literally the next slide about this. So you read my mind. So this method is great for reducing labeling costs, but when we think about kind of modern machine learning, especially deep learning, there's a number of practical challenges that come up. So the first practical challenge is that these models aren't necessarily simple to train, especially when we think about the kind of era of deep learning where we have these massive models that take a tremendous amount of resources to train, and computationally can be very expensive, and almost can be to the point, depending on the type of model that you're training, could be as expensive as the additional labeling costs and things like that. So I'd be curious, in thinking about kind of the diagram that we have here, what becomes computationally expensive when we think about these models? Yeah.
Just the training and doing inference.
Exactly, exactly. So first, in this first kind of point, we're going to focus on the training aspect of it. Training it after every single iteration becomes super expensive because of this computational expense. And now the way that people actually kind of get around this in practice, especially once like deep learning became a very popular kind of mode of machine learning, is we instead, rather than like retraining this model after every single example that we select to label, people instead will select a batch of examples at once and label them all at once so that they don't have to retrain this model. So if we go to this, the code that we wrote before, it's more or less going to be the same when we think about batch active learning versus kind of single example active learning. So we'll start off effectively in the same way. LR not, PR. So we'll start off in the same way, and then same looping process. This doesn't change at all. And then we train our model once now when we do this batch process. And then the only difference is that now, for one to some budget, or some budget as far as the batch that we want to label, we'll now just repeat this process of doing the argmax to get our X star and updating our data set. And everything else remains the same. So that is great. This solves this like first problem of like the models being really big and like addresses this computational bottleneck. However, one problem that we can find is depending on our selection strategy, we can end up with a lot of potentially redundant examples. So a very common form of active learning as far as the selection strategy is, we can write it here, is taking the entropy of the predicted probabilities for an example. Which is just the negative of the sum of the probability of a given label, given an example, and our current model, times log of that probability. Now this works really well in this kind of initial setting where we're selecting example one at a time and then we're updating. But can anyone think of a problem where if we just deal the uncertainty of the model, can we think of a data set or like a case where this could be problematic if we're thinking about batch?
Yeah, I guess if you're not updating your model in between, you might have similar examples that each have entropy that they're high, but they're kind of similar, so you're kind of doing the
Yeah, exactly. So if we have a data set that has a lot of redundant or near duplicate examples, like we could take, for example, any data set in the world, and if we were to just like multiply that every example like 100 times, then this batch active learning process actually saves us nothing. It'll be just as expensive as if we did the single iteration. So there's a lot of work that actually kind of goes into coming up with selection strategies that will not only take in kind of the uncertainty or the informativeness of like the model using something like entropy, but we'll actually try to select representative examples as well. Doing things like facility location and like greedy case centers in order to select examples that cover a space and that are representative overall, or just ensuring that there's some minimum distance between the labels that you've already the examples that you've already labeled in your data set and any new examples that you would add. So you can imagine adding an additional criteria here as like a simple fix for this of some kind of minimum threshold or heuristic distance from any example that's currently in your labeled set. But that solves one of the problems that you pointed out earlier, as far as like, training the model is very, very expensive. But another practical challenge is actually when we think about the size of this unlabeled data set, which when we think about modern data sets and data sets in practice, we can have really like large, massive, big data problems. So this comes up all the time in practice. When we think about recommendation systems, if you're at a large internet company, you might have millions or billions of images that are being uploaded by people every single day. And you want to be able to kind of identify maybe some new or interesting concepts. Maybe you're like care about fashion trends or some new viral like content, like a fidget spinner. You have all this data out there and actually trying to sift through it and process all of it to quantify the informativeness and the most kind of valuable example for your label can just be computationally intractable. And we see the same thing when we think about like autonomous vehicles. I know that Curtis on his like first lecture talked about autonomous vehicles and Tesla and their whole data engine there. So they also run into this problem where maybe for occluded stop signs or things like that, they want to find those examples and label them in order to kind of improve the model's performance, doing effectively an active learning strategy. But they can't go and process all of the data that's being collected by every single Tesla that's in the world. You actually have to be kind of more thoughtful and careful about the processing there. Otherwise, it would just be computationally too expensive. And similarly, we see this in e-commerce as well, if we're trying to actually deal with integrity problems or take down potentially bad content or bad postings. So for example, when I was at Facebook, it was at the beginning of the pandemic, and it was socially unacceptable or illegal to sell N95 masks because there was a shortage within the country. It became a real problem to actually be able to accurately identify those N95 masks and take them down. But that only represented a very small percentage of this like massive set of posts that are on Facebook's marketplace. So when we think about this challenge of having these like massive unlabeled data sets where the thing that we care about only represents a very small fraction of that, now we get into the second bottleneck, which is actually just processing all of the unlabeled data. So as an example of just like how computationally this can be, when I was at Facebook, we were working with 10 billion images, which were kind of roughly collected over like a 2-week span. And just to like run a single inference pass with a ResNet 50 model over 10 billion images took about close to 40 exaflops of computation, or about 40 GPU months using P100 GPUs, which is massive. Like no matter the cost of like the labeling for that single example, just the compute cost of alone of processing that amount of data is going to dominate your cost. And it's also going to be just way too slow if you have to wait days, weeks, or months in order to get an updated model to select the next example. So during my research, I actually tackled this problem working along researchers at University of Madison, Facebook, and at Stanford as well. And what we found is that even though you have these kind of massive unlabeled data sets, you actually don't need to look at all of that data in order to process it, especially as we have better representations from just foundation models and things like that. And instead, what we can do, and you'll actually implement this in the lab assignment that's associated with this class, is instead we can start the same way. So we'll have like a large pool of unlabeled examples, and then we'll have a small subset of labeled examples that we kind of initially use to train on and train a model. But instead of applying our selection strategy as we kind of described here to all of the kind of unlabeled examples and defining our candidate pool that way, what we can instead do is actually just take the currently labeled examples that we have, this kind of initial subset, and we assume that there's some kind of initial positive examples that you have for this class that you care about. And we can just find the nearest neighbors to that using standard similarity search. And we can effectively take those unlabeled examples that are closest to it and have that as kind of this neighborhood around those examples that we initially search. And then this is a much smaller kind of amount of data, and we can kind of keep iteratively doing this process. So as we label new examples, we can actually find their nearest neighbors in the unlabeled pool, update our pool kind of at every step of the way, and then we keep repeating this process. And the surprising thing is that, even though we end up only looking at a very small fraction of the overall data, we find that we can still reach the same amount of accuracy as we would have if we had scanned over all of the data. And this is, again, just kind of due to the power of the representations that we have in these large foundation models and things like that, and the representational power that we have now. We're actually very similar or even unseen concepts, like an N95 mask or a fidget spinner, are actually localized to a very small part of the latent space within this representation. So kind of going back to actually the example that I showed at the very beginning of this lecture, when we think about kind of active learning, doing this process on ImageNet as I explained, we can actually get to the same level of accuracy while only looking at a very small fraction of the data. So on ImageNet, looking at less than 10% of the unlabeled data and still getting to the same accuracy if we had performed active learning over all of the data. We see similar results for even larger data sets like open images, where there are 6.8 million examples. And we find that we can get, again, very close to the same mean average precision while considering only 1% of the data. And finally, we scaled it all the way up to 10 billion images. And we found, once again, that even at this scale, we can still get to the same level of accuracy or mean average precision while only considering less than 1% of the data, so 0.1% of the data. So this fundamentally makes it way more tractable to actually do active learning at these scales, which has been kind of a huge bottleneck to this kind of new wave of research and new wave of kind of just modern machine learning. And in the lab associated with this class, you'll actually get to see the difference firsthand, where you'll see kind of the process of kind of classical active learning on open images taking you minutes in between each selection round versus that going down to seconds and almost actually imperceptible between selection rounds. So you'll actually be able to implement and see the power there. And I'll pause if there's any questions about kind of these practical challenges or considerations within active learning. Yeah?
So you're saying the newest examples to what you've already selected or what you've already looked at?
The nearest examples to the ones that you've already labeled. Okay. Yeah. So effectively what is kind of happening here is that the candidate pool is growing over time and you're using the model's uncertainty to direct you closer and closer to the decision boundary in this kind of unlabeled space. Yeah. Great question. Yeah.
Isn't this kind of the opposite of analyzing closeness to examples you're doing in the batch?
Yeah. Yes. So super great question. Yeah, this actually, if you're doing batch active learning, you can actually still apply the same strategies that you would have for batch active learning transparently to this kind of seals approach, and then still get the best of both worlds. So you can prevent yourself from getting too close into the nearest neighbor's landscape, or too close into the nearest neighbor's kind of landscape, and actually force yourself to kind of go out to other examples. Also, with the initial seed set that you have, if those examples are in different places and things like that, it will create kind of you'll have a larger space to choose from. So you might choose one example from this kind of positively labeled example, another one from this negative, the neighborhood there. So it still can ensure that you have the diversity enough that you're not always selecting the same example over and over again or very, very close to it. And you can tune the amount of neighbors and the amount of neighbors that you look at to actually increase how far you can go in a single leap. So yeah, great questions. Anything else? All right. Sweet. So in the second part of the lecture, I'm going to kind of switch gears and thinking about, actually Corset selection and us compressing down these kind of large data sets into something that's more kind of more manageable. And this also comes up a lot in practice. So when we think about kind of large labeled data sets, it can come up in situations where we have systematic feedback. So for example, we might have people tagging friends in images. You might also having flagging emails as spam, where you're just generating a tremendous amount of labeled data from people all around the world using the system. Could be rating items or movies on like a website like Netflix. And also when we think about self-supervised models, when we think about these kind of language models, things like BERT, or in terms of computer vision, SimCLR, or Dino, these type of models where you actually define the label for every single unlabeled example. Here you have this massive, massive amount of data that's basically unlimited. But this can be actually really expensive to like go and process all of that kind of naively, especially since a lot of data in the natural world is often very, very skewed to a set of kind of small subset of like common cases. So what is Corset selection? So Corset selection is aims to select a small subset of the data that accurately approximates the full data set. So when we compare it to kind of the process that we had with active learning, it's actually operating in the reverse. So instead of starting with a small amount of labeled data, we actually have kind of a fully labeled data set or a lot of labeled data. And instead, what we do is we can train some smaller model or use some type of heuristic that's very cheap to compute over all this labeled data to say, hey, what are the most kind of representative or most informative data points for us? So you can imagine something like k-means clustering or anything like that to kind of identify these kind of representative points. And then we select that kind of subset of the representative points based off of our strategy there. And then we can train a model on that like final representative subset of data. And the crazy thing is that, you know, even though this data set is smaller and stuff like that, because data sets are often redundant, we can actually do this process without actually losing that much in terms of accuracy or other metrics that we care about. So as a practical example of this, we can actually like do this on a data set like CFAR10, which is, you know, CFAR10 is actually a relatively small data set and very well curated, and the fact that it has 10 classes, each one of those classes are evenly represented. But even in this setting, where here on the x-axis we have kind of the training time for a single P100 GPU, and then on the y-axis we have top one test error. We see that the gray dashed line represents the precision or the accuracy that we get with, or the error that we get with all of the data. If we were to train kind of a large, very accurate model on all of that data, it takes about close to 4 hours to train that model. But we can actually do this process of Corset selection, where we train some smaller, fast model, maybe that has fewer layers. So here we're training a ResNet 20 model rather than a ResNet 164 model. It doesn't get to the same accuracy that we get with this kind of larger, more accurate model. But what we can do is we can actually use that model. It only takes 20 minutes or 30 minutes for us to train. And we can actually filter out 50% of the data that is kind of the least valuable based off of our criteria here. And then we can train our large model on top of on that remaining 50% of the data. And what we find is that, you know, even though we're like using half of the overall data, we don't affect the final accuracy that we get with this large model of ResNet 164, and we actually can end up speeding up the end-to-end training time by 1.6x. So that's including training the small model, filtering out the data, and then training the large model on that subset, even in this very carefully curated data set of CFAR10. And this is actually kind of, in thinking about it, like only the tip of the iceberg in terms of like the different methods that we can use in order to like grow or compress data sets. So we talked about active learning as kind of a generative process for kind of figuring out what data points to label from some large pool of examples, and Corset selection as a way to distill it down. But even within active learning, there's many different variants of active learning. We talked about very simple binary classification setting here, but there's a bunch of different selection strategies and things to think about in different domains. There's also the possibility of doing generative active learning, where rather than having a pool of examples, you know, we can actually generate the examples that are the most informative for us to label. Especially as we think about kind of recent improvements in generative AI, this can actually enable you to save in terms of computational costs and like the size of your unlabeled data, and speed things up even further. There's also a problem called active search, which is a sub-area of active learning that's particularly used in drug discovery, where we don't care about model performance at the end of the day. We just want to find as many positive examples, as many successful drugs as possible. And as a result of that, there's kind of a whole separate set of like field of study and set of selection strategies and ways for framing that problem there. There's also a notion of hard example mining where you're using kind of other heuristics or methods in order to say what are like kind of the most difficult examples or most valuable things to include into your data set, which is commonly used in recommendation and search problems. We also have this whole notion of curriculum learning, which is the process of not only selecting which examples to label, but also what order do you train on those examples and show them to the model. So creating a full curriculum of examples to study from, and much more. This is kind of a rapidly growing field that's only becoming more and more important as we think about just the importance of data, creating very well-crafted data sets, and solving these problems. And I blew through the time in that lecture, but this is like the immediate material that I prepared, so thank you all. If there's any questions, I can also jump back and dive into more detail on things.
This seems very suitable for image classification.
Yeah.
How does this apply to language models and something like ChatGPT?
Yeah.
If you are choosing a subset, can you losing a lot of useful data?
Yeah, so super great question. So like when you think about like ChatGPT or any of these large language models, they also have to think about careful like data set curation. Like thinking back to like the original GPT-3 paper, if you read it carefully in the way that they structured the data set, they had like a lot of like general internet data, but actually that wasn't the most valuable data for them to use. They actually upsampled examples or data points from Wikipedia and things like that were more carefully curated and refined in terms of the examples. So being able to actually kind of inform like, hey, maybe you don't need all of like this web data that's like inherently very redundant. Maybe you can take a core set of that and instead focus kind of more attention on the examples from this kind of curated, more informative data set like Wikipedia. So even in like the case of these large language models, there's actually a lot of work that goes into curating the data set, shaping the data set for it to be valuable. And originally when you think like GPT-3 before it became ChatGPT, also had the problem that, you know, they weren't, individual examples can also be very bad or provide kind of harmful biases in it. So you can also do active learning strategies and data selection strategies to kind of mitigate that bias and to make sure that you have kind of representative examples. So maybe you want to, you find that like you're struggling to like have the notion of a doctor, but you could combine it with some type of generative example to be like, hey, maybe it has an association of a doctor being a man. You can actually be like generate a cross or like generate examples where the doctor is a woman or of a different kind of ethnicity or background or things like that as well. So, does that answer the question? Yeah. Awesome. Sweet. And then thinking about the lab assignment, which I believe should be posted on the website, what you'll do in that process, actually, which I forgot to mention about, was you'll actually go through this process of implementing active learning on this one-dimensional line. So you can actually see the speed up firsthand, actually go through this process. And then, kind of after doing that as like a nice warm-up example, go to a really large data set, go to open images and actually implement active learning there and deal with just the computational bottlenecks of that, even with a very small kind of model, where you'll actually implement seals and you'll see a speed up of an order of magnitude in terms of the time that it takes to select individual examples. But, yeah. Awesome. Any other questions? I can also talk, let's see, there's a lot of other pieces of kind of interesting areas in active learning and research as far as like different selection criteria, different problems and things like that. This whole computational aspect of it, of being able to create these data sets, is actually kind of top of mind as we think about kind of expanding to these large data sets and thinking about just the ever-growing thing of GPT, of these like foundation models, large language models, and things like that. But yeah, it's a super exciting area of research, and happy to chat with anyone in like the kind of 10 minutes or so that we have left in the lecture. So thank you all.